Good day everyone! Today we are going to present to you the lipids metabolism and its function in our body. I am Hanigan Perfinian and along with my groupmates. So what is lipid metabolism? Lipid metabolism involves the synthesis and breakdown of lipids crucial for energy production and cellular function. It encompasses the oxidation fatty acids for energy and the creation of new lipids, playing a vital role in maintaining cellular health and signals. First, the objectives. The objectives of this discussion is discuss the relationships between lipogenesis and citric acid cycle intermediates. Second, what is fate of fatty acid generated acetyl-CoA, and discuss the relationships between lipid and carbohydrate metabolism. Last is the B vitamins and lipid metabolism.
Relationships between lipogenesis and citric acid intermediates. Lipogenesis is the process of synthesizing fatty acids from acetyl-CoA and is intrinsically linked to the citric acid cycle, also known as the Krebs cycle or TCA cycle. Understanding this relationship is crucial for comprehending how the body manages energy storage and utilization. Here are the key points regarding the relationship between lipogenesis and citric acid cycle intermediates. Number 1. Role of acetyl-CoA. It is a source of building blocks and the primary substrate for lipogenesis. It is derived from the breakdown of carbohydrates via glycolysis and fatty acids through beta oxidation. Entry into the citric acid cycle. Acetyl-CoA enters the citric acid cycle where it is oxidized to produce the energy in the form of ATP and ADH and FADH2. Number 2. Intermediates of the citric acid cycle. Citrate is a key intermediate. When energy levels are high, excess acetyl-CoA can lead to the accumulation of citrate in the mitochondria. Citrate can be transported out of the mitochondria and into the cytosol, where it is converted back to acetyl-CoA and oxaloacetate by the enzyme ATP citrate lyase. Regulation of lipogenesis. The conversion of citrate to acetyl-CoA in the cytosol is a critical regulatory step in lipogenesis. High levels of citrate signal that energy is abundant, promoting fatty acid synthesis. Number 3. NADH production. Source of reducing power. Lipogenesis requires reducing equivalent in the form of NADPH. The conversion of citrate to acetyl-CoA generates oxaloacetate, which can be converted to malate and then to pyruvate, producing NADPH in the process. Malic enzyme. The malic enzyme catalyzes the conversion of malate to pyruvate, generating NADPH, which is essential for fatty acid synthesis. Number 4. Integration of metabolic pathways. Energy storage versus energy production. The relationship between lipogenesis and the citric acid cycle reflects the body's ability to switch between energy storage, which is lipogenesis, and energy production, which is the citric acid cycle, based on nutritional status and energy demands. Hormonal regulation. Insulin promotes lipogenesis by enhancing the transport of glucose into cells, increasing the availability of acetyl-CoA and citrate, while glucagon and epinephrine promote the breakdown of stored fats for energy. Number 5. Clinical implications. Metabolic disorders. Dysregulation of the relationship between lipogenesis and the citric acid cycle can contribute to metabolic disorders such as obesity, insulin resistance, and fatty liver disease. Therapeutic targets. Understanding these pathways can help identify potential therapeutic targets for managing metabolic diseases by modulating lipogenesis and energy metabolism. Conclusion. The relationship between lipogenesis and citric acid cycle intermediates is a vital aspect of metabolic regulation. By understanding how these pathways interact, we can gain insights into energy balance, fat storage, and the implications for health and disease. This interplay highlights the complexity of metabolic networks and the importance of maintaining metabolic homeostasis.
Now let's talk about the fate of fatty acid-generated acetyl coenzymes A. Acetyl coenzymes A is a central metabolite in energy metabolism and is generated from the breakdown of fatty acid through a process called beta oxygenation. Once formed, acetyl coenzymes A can enter several metabolic pathways depending on the body's needs and the availability of substrate. Here are the primary fates of fatty acid-generated acetyl coenzymes A. First one, entry into the citric acid cycle or Krebs cycle. Next one is ketogenesis. In situations where carbohydrates availability is low, for example, fasting, low carbohydrates diets, or uncontrolled diabetes. Next is acetyl can be converted into ketone bodies in the liver. Ketone bodies serve as an alternative energy source for various tissues, including the brain, during prolonged fasting or carbohydrates restriction. This process is important to maintain cellular membrane integrity and producing steroid hormones. The fate of fatty acid generated from fatty acid oxygenation is influenced by the metabolic state of the organism and the availability of other substrates. It can either enter the citric acid cycle for energy production, be converted into ketone bodies for alternative energy sources, be utilized for fatty acid synthesis when energy is abundant, or used to cholesterol synthesis. The flexibility of acetyl coenzymes A utilization allows the body to adapt to varying nutritional and energy demands.
Hi, this is Christopher Mark Parafina of 1A. My topic is about relationship between lipid and carbohydrate metabolism. As we know, lipid and carbohydrate metabolism are interconnected processes that play a crucial role in energy production and storage in the body. Lipids such as triglycerides and cholesterol can be synthesized from carbohydrates through pathways like de novo lipogenesis. Conversely, carbohydrates can be converted into lipids when there is an excess of glucose. Here's a detailed overview of the relationships between lipid and carbohydrate metabolism. First, we have lipid catabolism and carbohydrate connection. We have beta oxidation. Fatty acids undergo beta oxidation in the mitochondria, breaking down into acetyl-CoA, which enters the citric acid cycle or the Krebs cycle. Energy production, the process generates NADH and FADH, which are utilized in the electron transport chain to produce ATP. The second one is the synthesis of lipids from carbohydrates. Triglyceride formation, where glycerol 3-phosphate derived from glycolysis combines with fatty acids to form triglycerides, a major energy storage form. So when it comes to cholesterol synthesis, cholesterol is synthesized from acetyl-CoA, linking lipid metabolism to carbohydrate metabolism through intermediaries derived from glucose. Third is interconversion of metabolic pathways. First is glycogen storage. Excess glucose is stored as glycogen in the liver and muscles. When energy is needed, glycogen is broken down into glucose, which can enter glycolysis. Next is amino acid utilization. In states of excess or starvation, amino acids can be converted into glucose or intermediaries that enter the citric acid cycle, linking protein metabolism to carbohydrate and lipid metabolism. fourth is regulation and homeostasis. Feedback mechanisms, which includes metabolic pathways that are regulated by feedback inhibition, ensuring a balance between lipid and carbohydrate metabolism based on the cell's energy needs. So, next is energy demand response. The breakdown of glycogen and triglycerides is influenced by energy demands, allowing the body to adapt to varying nutritional states. So to summarize, lipid and carbohydrate metabolism are not isolated. They share intermediaries and pathways, allowing for efficient energy utilization and storage. The integration of these metabolic pathways is essential for maintaining energy homeostasis in the body.
Now let's talk about B vitamins and lipid metabolism. B vitamins, particularly B12 and B6, are crucial for lipid metabolism, influencing fatty acid synthesis and oxidation, and are essential for maintaining healthy lipid profile and preventing cardiovascular diseases. Key function of B vitamins in lipid metabolism. B1. Thiamine, involved in the conversion of carbohydrates into energy, which indirectly supports lipid metabolism. B2. Riboflavin, plays a role in the metabolism of fats and carbohydrates, aiding in energy production. B3. Niacin, essential for the synthesis and NAD and NADP, which are crucial for fatty acid metabolism and cholesterol regulation. B7. Biotin, involved in fatty acid synthesis and gluconeogenesis, supporting overall metabolic processes. B9. Folate, plays a role in the synthesis of nucleic acids and amino acids, which can impact lipid metabolism. B7. Biotin, involved in B7. Biotin, involved in fatty acid synthesis and gluconeogenesis, supporting overall metabolic processes. B9. Folate, plays a role in the synthesis of nucleic acids and amino acids, which can impact lipid metabolism. B12. Cobalamin, critical for metabolism of fatty acids and amino acids. Deficiencies can lead to lipid accumulation and metabolic disorders. Consequences of B vitamins deficiency. Lipid accumulation. Deficiency in B vitamins can lead to the accumulation of proteinogenic cholesterol and fatty acids, particularly noted in studies involving apoinosine mice. Increased cardiovascular risk. Disruption in lipid metabolism due to B vitamins deficiency can elevate the risk of cardiovascular diseases. Metabolic disorders. Long-term deficiency may contribute to metabolic syndrome and related health issues.
As for conclusions, the relationships between lipogenesis and citric acid cycle intermediates highlight the intricate balance between lipid and carbohydrate metabolism. Acetyl-CoA generated from fatty acids serves as a crucial substrate for both energy production and lipid synthesis. This interplay is further influenced by B vitamins, which are essential cofactors in metabolic pathways. That's all. Thank you.